Hi and welcome to the Foundations course lesson 1, Data Summary Measures. Today we're going to look at different types of data, independent versus dependent data, data summary measures, and the different types of data graphs that are often used in medical research. It will be a very easy intro into this Foundations course, but I think it's important to increase complexity over time and start with the very basic building blocks. So let's start with looking at variable. In medical research, we often talk about variables. What does it actually mean? Well, a variable is an information containing entity, and it should be collectible as data. And moreover, we should expect certain between subject variability. But we can also subdivide variables according to their function. So in medical research, we're interested in outcomes, and an outcome is actually a variable. We usually measure and collect lots of other data that we try to use to explain that outcome. So those other variables are called explanatory data and independent variables, whereas the outcome is called dependent variable, since it should depend on the input of the explanatory data. Certain synonyms are often used, like predictor or covariate, but they actually refer to the function of independent variables within certain types of analysis. A very basic distinction can be made to differentiate different types of data. And the first distinction is categorical versus numerical. And within the categorical type data, we can distinguish nominal and ordinal data. We'll come back to what that actually means. And on the numerical side, we can distinguish continuous and count data. Now let's look at nominal categorical variables. This is the simple categorical type that we tend to think of, for example, with only two categories like yes or no, or gender, male, female. And those, if they only have two categories, they are actually referred to as discrete or binary categorical variables, but they can contain many more categories. But the essential thing is that there is no rank between the different categories. Whereas in ordinal categorical variables, there is actually a rank. And a lot of score systems are developed in medical research, like the head injury severity scale, the Glasgow Coma scale, the APGAR score, things like that, that contain different categories that differ from each other with regards to disease severity. So, for example, in a 10-point pain scale, you have a score of 0, which is no pain, and 10 is like intolerable, unimaginable pain. And all the numbers in between, they refer to an increase of that pain. Now, the continuous type of numerical variables is the typical type of numerical variables that we tend to think of. And the essential thing is that we could theoretically measure these types of variables with infinite precision. For example, systolic blood pressure measurements. Well, actually, we tend to round off data as whole numbers in medical research, but we could theoretically measure blood pressure with infinite precision if the measurement device is good enough. So we could collect data with multiple digits after the comma. Count numbers refer to a type of numerical variable that relates to the count of events within a period of time. Only whole numbers make sense. And if we summarize this in categorical data, we have nominal data. And here's a little mnemonic. Nominal stands for no order, so they are unranked. And ordinal categorical data, and ordinal stands for ordered or ranked. And within the numerical type of data, we can distinguish continuous data, which are exact numbers, and count data, which are whole numbers. Now, it's also important to distinguish independent and dependent data. Most data in medical research are independent because they originate from unrelated sources. But sometimes we measure things in the same individual, same organ, same patient, same hospital, and we have to carefully ask ourselves whether these data are actually independent or they could be related. And those data are also called clustered data. Clustered or dependent data require totally different analysis than independent data. If we've measured 2 data points in the same patient and then measure them in another patient, we will see that the difference between the patients, or the between patient variability, will oftentimes be much larger than the within patient variability. And so we cannot just add those 4 data points to each other and then treat them as independent. Well, we tried to use different types of data summary measures to get a good idea about the distribution of our data points in a cohort. So we have to distinguish between central tendency measures, which tell us something about where the most frequent or the middle measurement lies, and the measure of spread. So what is the clustering of data around that central tendency measure? And within normally distributed data, we work with the mean as a central tendency measure, which is simply said just an average. And we use the standard deviation as a measure of spread. Whereas in skewed data, data with many outliers, we want to work with the median as a central tendency measure and the range as a measure of spread. The mean is the average of a continuous variable, and here's the mathematical denotation of the sample mean and the population mean. And later in this course we will explain the difference between sample and population measurements. But the sample mean is the thing that we tend to work with in our data analysis, and it's denoted by a bar over x is the sum of x, and x is actually just the value of an observation in an individual. So we take the sum of those values and we divide it by n, which is the number of observations. And the population mean can be calculated in the same way, but is denoted by the Greek letter mu. And we shouldn't use means in skewed data or data with extreme outliers, and maybe even not in count data, because the mean is very much influenced by outliers. And the standard deviation is a measure of spread that belongs to the mean. And you can think of the standard deviation as the average distance of your observations to the sample mean. It is denoted by a small letter s for the sample standard deviation, and it is the square root of a ratio. And that ratio is the variance. We'll come back to that in just a second. But if we look in detail to that ratio, we see that it's the sum of something squared divided by n, the number of observations, minus 1. And that value that is squared is the distance between the value of an individual observation to the sample mean. So it's the distance between the values that we observe and the sample mean squared, and then the sum of all those squared differences divided by n minus 1, and then the square root of that ratio. And the population standard deviation is denoted by the Greek letter sigma, and it's almost equal. It's just that we don't divide it by n minus 1, but we divide it by n. And the same goes for the standard deviation as the mean. We shouldn't use it for skewed data, data with extreme outliers or counts. I already briefly hinted at the variance, but there's a very close relationship between variance and sample standard deviation, because the variance, as you can see, is the small letter s squared. So it's actually the standard deviation squared. And why is that? Because the variance is that ratio that we talked about. And so we can also reverse the relationship by saying that the standard deviation is the square root of the variance, and vice versa, the variance is the standard deviation squared. Now, I'll give you an example of how to calculate a standard deviation. Let's say we have measured systolic blood pressure in 10 individuals, and their values here are denoted in a graph. And I've plotted the mean, which is the sum of all the values that we have observed, so the sum of those dots, divided by n, which in this case is 10, and then we'll have a sample mean of 120. Now, the first next step is that we want to know what the distance of the observations is towards the sample mean. And those distances are called residuals. So this orange bar is the residual because it's the distance of value measured in patient 1 and the sample mean. So this patient has a lower value than the sample mean. This one is close to the mean, this one is a little higher, a little lower, and so on. So what we can say mathematically is that the residual is x, the value of the individual, minus bar over x, which is the mean. And if we want to sum all those values up, we have a problem because negative and positive values tend to cancel each other out. And we only want to know what the absolute value is of the residuals. So what we'll do is we'll sum the square of the residuals. So we take this difference, take the square of that, take this difference, take the square of that, and so on, and then sum all those values up. So it's denoted by the sum of the residual squared, sum of the square residuals. And now we can easily calculate the sample variance because we have the sum of the square residuals and we divide it by n minus 1. And what that says is a little complicated because we now have a measure that is the distance between the observations and the sample mean, but it's measured in squared millimeters of Hg. So if we want to know the sample standard deviation, our last step is to take the square root of that variance, and then we'll have our standard deviation. Now, the median is a lot simpler. It's a central tendency measure for non-normally distributed data. And it's actually the observation that lies in the middle of all the observations when we rank them by order. And mathematically, you can say it's the n plus 1 divided by 2 value of the ranked observations. And this formula actually solves the problem of calculating a median in even and uneven number of observations. So we can use them in non-normally distributed continuous variables, skewed data, and counts. And the range is actually the measure of spread that is calculated by taking the range of the observed values. So we take the maximum collected value and the minimum collected value, and that difference is the range. And as we already said, the mean and standard deviation belong to each other, and the median and the range belong to each other. And in scientific publications, the notation used is oftentimes this for the mean and standard deviation, and the median and the range as denoted here. Now, to finish this lesson, we'll talk about data graphs. But first I want to caution you a little bit, because it's very easy to trick someone with a graph or a chart. So don't be fooled, and always ask yourself the following questions. What is displayed? So what are the labels on all the axes that I see? What is the unit of measurement? Are the axes truncated or scaled? And are all measurements displayed, or are there outliers or that are just not shown, or is this whole graph just a selection of patients? Now let's start with the box plot. It looks a little bit like this, and we already said that the minimum and maximum value are the range, and so in a box plot there's a line that goes from the maximum and the minimum value, and then the actual box is plotted within that line. And the line within the box is the median. It's not always in the middle, it can also be higher or lower. And the median is the same as the second quartile or the 50th percentile, because it's just the middle observation. But if we talk about percentiles, we can also look at the 25th percentile and the 75th percentile, or the first and the third quartiles. And those are actually the boundaries of the box below and above the median. So the distance between the first and third quartile, or the 25th and 75th percentile, is the interquartile range. Now, another way to display continuous variables is using a histogram, where you can denote here on the y-axis a frequency of a value, and then on the x-axis the actual value that is measured. So here you can see an example of a normally distributed data type, where in the middle we see the most frequently observed outcome. And in this graph we look at frequencies, but we can also look at the probability of that outcome within all the observed values. And then you get a probability density function, which you can denote as a mathematical equation. And the area under this graph should be 1 or 100%. Scatterplots are used to display the relationship between two continuous variables, and it's common use to plot the explanatory variable on the x-axis and the dependent variable or the outcome on the y-axis, and then just denote all the scatter dots values of a dependent variable and the explanatory variable that goes with that. And I want you to understand that oftentimes a line is fitted to describe this relationship, but that's actually part of an analysis. It's called a linear regression line, and it's not part of the graph itself, because this line is an approximation of the relationship and oftentimes doesn't perfectly fit to the data. Now, a bar chart is used to display the distribution of categorical variables, and it's very easy to see differences between frequencies of occurrence between categories and subcategories. Like in this case, we have 3 different categories, and then we can compare subcategories with the blue and the green value. Here you see review of the number of animals within 2 different zoos, and because they have different colors, we can easily compare the number of giraffes, orangutans, and monkeys in the San Francisco and LA Zoo. You can also add all categories up and then say the total of that value is 100%, and I just want to see the relative portion of all categories within my data set, and then make a pie chart just like this. All right, that's it for the first lesson on data summary measures. Great job hanging in there, and get ready for probability distributions.